discovered in Chapter 6, drilling for hydrocarbons requires a lot of technical know-how, precision tools, and a lot of money. It is dirty, it is dangerous, but we still do it. Although there is no guarantee we'll find hydrocarbons. But then again, we might. Drilling, although technically challenging, just creates a hole in the crust. In this chapter, we need to evaluate that hole to determine if that well will be a commercial oil or gas well or just another dry hole. We'll describe how we measure, sample, and test the actual rock formations and their properties at the various depths of the hole as we drill downward. We'll show how we are able to use these measurements, samples, and test evaluations at different stages and depths of the drilling program to help us identify any reservoir rock that is present. Once identified, we'll add this information to the mud log as we drill, and then compile another more detailed electronic log after TD or total depth has been achieved. Along the way, we'll continue collecting samples and performing tests that help us determine the porosity, the permeability, and saturation, or types of fluid, present in that rock. Next, we'll determine the depths, size, thickness, temperature, and pressure of the rock formation. Finally, by using the data from all of these procedures that help us evaluate the formation rock, and from the results of the seismic tests conducted earlier that gave us this area, we'll be able to calculate if there are enough commercial quantities of hydrocarbons present to continue the development of the well. As you might guess, each of these measurements, samplings, and tests require time and money. Because it is usually the team of engineers who decide what procedures to run, it is they who must justify not only the costs of these procedures, but also the downtime in the drilling program. Although the industry is fast improving the technology to run procedures during drilling in what is called measuring while drilling, or MWD, and logging while drilling, LWD, many times it is still necessary to round trip in and out of the hole with specialized equipment. Remember, round tripping is when the drill string with the drilling bit and all of the stands of pipe are pulled out of the wellbore for testing and then put back in when it is finished. The information we learn from the different procedures will help guide us in deciding whether or not to abandon or complete this well. Regardless of whether we find the next big reservoir or are faced with a dry hole, our data, acquired at a lot of time and expense, will not go to waste. It will be uploaded into powerful computers that can then be used to more accurately help predict where to drill the next wildcat or development well. Let's look at some of the traditional ways we monitor data, collect samples, and perform tests so that we can evaluate what's in the formation. First, during drilling in what is known as open hole wells, or wells that have not been prepared for production, data from the mud log is compiled by the driller, the mud logger, and the site geologist. If zones of interest are detected, then samples from cores are collected. Next, while usually still in the open hole phase after TD has been reached, drill stem tests, DST, wireline formation tests, WFT, and open hole well logs are performed and interpreted. Finally, the last test, the initial potential IP test, is conducted after the well has been completed and equipped in what is known as cased hole or closed hole, but before the well has been prepared for production. This very important test allows reservoir fluid volumes or flows and pressure measurements to be accurately determined. Let me point out here that because very little data is available in wildcat wells, the testing emphasis for them is somewhat different than for development wells. For example, in wildcat wells, more core samples are collected to help identify rock formation, while in development wells, more drill stem tests help identify the various target zones and their characteristics. When gathering data from wildcat wells, therefore, the most critical step is to pinpoint potentially productive zones as they are penetrated. This can be a very trying task. Drilling through an oil or gas zone can easily go unnoticed because the weight of the mud column can prevent reservoir fluids from entering the wellbore, thus obscuring the data. The company representative, the site geologist, and the mud engineer must be very vigilant. They closely scrutinize the rock cuttings or rock pieces that have been crushed out of the formation by the drill bit and sent to the surface with the returning mud through the annulus, and make sure that this data is accurately recorded in the drilling operation log. A particular challenge when drilling development wells is correlating new data from a particular well with existing data from previously drilled nearby wells. Because rock structures and formations can change dramatically from one location to another, it is not uncommon to encounter conflicting, confusing data. An example of this might be when the porosity of the rock for a particular zone changes from one well to another. When the geologist spots these variances or differences, he'll be called on to explain this heterogenesis in the subsequent constructed models. Now, let me explain some methods used to collect data to evaluate both a wildcat well and development wells. In each method, we'll discuss how the need for different data will influence how the data is handled and analyzed. In this chapter, we'll limit our discussion to open hole wells. We'll talk more about closed hole or cased hole wells in the next chapter. From the day we spud in, we begin collecting drilling data. The record that we make is called the drilling operations log or mud log. This continuous foot by foot or meter by meter record of the hole as it is being drilled is referred to as the mud log. All important data gathered from the cuttings and from the mud returns as well as from the drilling operations are plotted against the depth on the same strip chart of log so that they can be compiled on a chart. This drilling operations log is a record with three main inputs from the driller, the mud logger, and the site geologist. Let me explain each input in a little more detail. We'll start with the input from the driller. While rotating the Kelly, the driller measures how fast or how slow the Kelly goes down. For instance, when drilling through hard rock, the Kelly descends more slowly than when drilling through softer rock. The speed of the Kelly's descent is known as the drilling rate. The drilling rate is recorded on the log as the number of minutes per foot penetrated, rate of penetration. Knowing this speed helps identify the type of rock that is being penetrated and gives a general indication of the porosity of that zone. Hard rock, for example, is usually associated with shale or other cap rocks, while softer rock is associated with sandstone or limestone, which can be oil or gas-rich reservoir rock. When the bit exits the non-porous hard rock and enters softer porous rock, the recording instruments in the log show this jump, as you can see on this illustration. This jump is called the drilling break. When this happens, the driller raises the drill bit a few feet, breaking off from the bottom while continuing to rotate and circulate mud. This circulating mud scoops up the last of the cuttings and sends them to the surface. This is called bottoms-up circulation. These cuttings from the last turns of the drill bit are then analyzed by the site geologist and are instrumental in helping to determine future steps in the drilling program. For example, the geologist may make a determination to core the next section of rock to be drilled based on his analysis of these cuttings. In addition, the driller keeps a running count of the number of lengths or stands of pipe that have gone down into the hole. Using pipe stand measurements to determine exactly at which depths different types of rocks are encountered, the driller can provide the data that allows the depths and the thickness of hard and soft rock to be tabulated. The next input is information about the mud compiled by the mud logger. His job is to constantly monitor the mud for oil and gas shows. He does this in a variety of ways. In addition to checking for any oil shows that may have migrated to the surface with the mud or that floats in the mud pit, he also exposes mud samples to ultraviolet light that will show fluorescence if oil is present. With gas, he is looking for gas shows that bubble out of the mud at the surface. Not only is he on the lookout for potentially hazardous kicks, which is gas that has entered the wellbore from the formation, he also uses a gas chromatograph to spot signs of gas that can be measured as they are released from the pores of the rock as it is drilled. The mud logger carefully tracks and inputs both the depth and the approximate locations of promising oil and gas shows on the log. The third input comes from the site geologist, who identifies and studies the cuttings that are filtered out by the shale shaker as the cuttings are brought back to the surface in the mud stream. He collects samples of these cuttings every few feet of drilling in order to examine them under a microscope. In studying these samples, he describes their lithology and porosity in detail and determines whether oil shows, gas shows, and hydrocarbon odors are present. For example, when describing the lithology, he examines the rock to define their characteristics or properties like color, size, shape, porosity, mineral identification, etc. These rock type descriptions then allow him to hypothetically place these cuttings in the appropriate zones in the stratigraphic column. Correlation will also be necessary if data from previous drilled wells is available. As you may expect, when working with these cuttings, there is usually some guesswork in analyzing and correlating all this data from the different inputs. This guesswork, in fact, can lead to errors or miscalculations in depicting the various compositions of the layers and their depths in the stratigraphic column on the mud log.